this. And this picture is actually taken from there. So if you get bored, please feel free to get out and enjoy this scenery. I will talk about machine learning for bounce calculation. And I'm Ryusuke Jinno from ICTP. This talk is based on one paper by me. And before going into physics, I would like to have some self-introduction. I'm Ryusuke Jinno, and I got PhD 2 years ago in Tokyo, and I spent some time in Japan. And the main message is that I will be moving to Germany, so I think I will have better access to European institutes from next April. And also I have a bit different background than yours. My research interest and it works kind of inflation and preheating. Preheating is particle production in process after inflation, or gravitational wave production in late time universe from first order phase transitions. And I came up with an idea of using machine learning when I'm working on this gravitational wave stuff. So that's why today I'm here. So yeah, today's topic is machine learning. Okay, now this is my talk plan. I will first give a very brief introduction about machine learning, especially neural network, though you may know much better than me. And then I will explain how I can use machine learning technique to tunneling problem in quantum field theory. And this third section is kind of detail, data taking, machine setup, training process, and results. And then I will finally summarize my talk. Okay, so, well, we all know that machine learning is now very popular. Its application stretches, for example, from what? Big data, customer retention, or game AI, blah, blah, blah. And a simple-minded man like me wonders, like, can I apply this technique to problems in high-energy physics? But before applying machine learning technique, we have to know what it is. So this is a summary for the terminology. Machine learning is here, but the larger area is covered by this artificial intelligence, AI, which is defined as machines that can perform tasks that are characteristic of human intelligence. This is a very broad definition, and machine learning is kind of subset. This is defined as a way of achieving AI, which means that learning without being explicitly programmed. So machine learns without being taught details. And neural network is further subset of this, and I will use this neural network. And this is machine learning with artificial neurons, which I will explain later. And I will not use this deep learning or deep neural network, which is much more advanced topic. I will just use simple neural network. So let me explain how powerful neural network is. And this is well-known spam email example. So, okay, I will first explain linear problem. Suppose that you have many, many emails, and suppose that you want to classify these emails into spam and not spam, and suppose that this is your data, and you come up with an idea, let's say, X1 is number of discount in the email, and X2 is number of luxury in the email, and suppose that after your classification, the distribution is like this. So the question is that let's find A and B such that X2 equals to AX1 plus B is the boundary of this spam and not spam. If you can do that, it means that you constructed a very good machine for the classifier, so you don't have to do it yourself. And in this specific case, the answer is really simple because the distribution, this boundary is, as you can see, this is linear. So this is called linear problem, and a good solution is found very easily. But the problem occurs when the distribution is like this. So in this second case, it's difficult. It's hard to find a good line to separate these two regions, because now the boundary is not linear. So this is, there's no good solution for this case. But in this, again, in this specific case, you may find some change of variables, like let's define r as the radius measured from this origin, and theta as the angle from this x1 axis. Then you will find that all your data becomes like this. So now the boundary between this spam and not spam is linear. So now you find a good solution. So, well, now you find a good solution, so everything is fine, you may think. But this is not good, because this is called feature engineering. In this specific case, you're successful. But the problem is that you cannot always find such good quantities. So the question is, any good strategy for this kind of problem? So good strategy to capture this original non-linearity. That's the problem. And what I would, the answer is neural network. This is very useful in capturing non-linearity. And this is some picture taken from web on biological neuron. And okay, this orange, okay, I'm not expert of this biological neuron, but each neuron collects electric signals through this junction synapses. And the important point is that when the total signal exceeds a threshold, electric signal is sent to the next neuron through this red axon. So we can mimic this structure. That's the artificial neural network. Okay, diagrammatic notation is like this. Here, x1, x2 to xn are your inputs. This is just real numbers. And you multiply weights, w1, w2 to wn, to these values. And let's put the summation here. And then, in order to obtain the output, you multiply, you operate this nonlinear function to this sum, and that's z. Very simple. And the equation is like z output is a nonlinear function of this summation, weight times, input times weight. And here, I didn't show, but there's one parameter bias. And for this nonlinear function, f, it's now found that this so-called ReLU function, rectified linear unit function, works very well. So I will just adopt this. This is single neuron. And okay, now we can construct a neural network. That's a network of artificial neurons. So our previous structure, neuron, is here. And all this collection, all this bunch of neurons makes this neural network. This is a kind of brain. Okay. And at the equation level, this is like the same as before. This x1 layer, the value x1 is just a nonlinear function of this input times the weight matrices, weight matrix plus bias, and the same for the next step. And finally, we get this x out here. So this is just linear algebra plus a bit of nonlinear function, so very simple. But so far, all these weights and biases are just kind of random numbers. So if we input something here, the output is also output is just random numbers. So that's nonsense. So we have to train this neural network. And in this talk, I adopt so-called supervised learning, the simplest training scheme. Okay, this is supervised training. And okay, let me explain how to train the neural network with supervised learning. Suppose that we have many combinations, many data of x input, and true value of x output. This is kind of answer. And then, if we input this X into machine neural network, we get output. So we can define how poorly the machine predicts. That's called the error function or loss function. And I adopt this L1 norm. There are several choices for this error function. Some people use squared here, but I will just use this absolute value linear error function. And finally, the training of neural network means the update of bias W, weight W and bias B using this error function. So this is just gradient descent method. The weight enters in this output, and this weight is updated by this gradient descent, and bias is also updated with this gradient descent. And as a small note, there are more sophisticated algorithms like ADAGRAD or ADAM, but I will not explain it. In my paper, I used ADAM, but I will not explain it. So now let's see how powerful a neural network is. This is just a toy example. I generated 100 points of X out using this function. So X out is fourth order polynomial of X in, and it's here. And I trained my neural network with this laptop using 2 hidden layers, 20 neurons per each, and train for 10 seconds. And this machine now fits all the input data like this. So the message is machine learning or neural network is very useful in capturing this nonlinearity. So I will use this in QFT tunneling problem. Okay, before going to tunneling problem, the same story applies for this image recognition problem. The image classifier, so suppose that this is my cat and this is my dog, and we know that machine works very well. Neural network perform very well in classifying these 2 pictures. And the classification means giving a level for cat or level for dog for each picture. And this can be regarded as a nonlinear relation between input and output. And in this image recognition case, the input is just a sequence of these numbers. Imagine grayscale image, and then we input this grayscale value here, and then we get output 0 or 1. Precisely speaking, the output is kind of so-called logos, but that's detail. And also, actual image recognition is not this simple. So that's explained in the previous, explained by previous speaker. We can use convolutional neural network, but this is the main kind of the main point of image recognition. So let's use this to let's apply this to machine tunneling problem in QFT. That's this. This is your potential, and suppose that your scalar field is trapped at the force vacuum. Then at some point, this scalar field feels that it's in the force vacuum, and then experiences the tunneling to the true vacuum. But why? Why should we care about this tunneling problem? I myself is working on gravitational wave physics, and as you may know, gravitational waves from black hole or neutron star binaries have been already detected maybe 2 or 3 years ago. And okay, this detection opened up the era of gravitational wave astronomy, and some people in HEP-PH phenomenology expect that the next is gravitational wave cosmology. And it's well known that this kind of tunneling process in the early universe gives bubble dynamics. So if this tunneling occurs, small bubbles nucleate inside the universe and they expand. And and eventually these bubbles collide with each other, and during that process, gravitational waves are produced. And if we are lucky enough, we can detect these gravitational waves in near future by space interferometers like LISA, DeSigo, BBO. So if we are lucky enough, the signal comes like this. This is frequency versus gravitational wave amplitude plot. So if we are lucky, we can measure, we can observe it. So that this is important. And this physics have been attracting many people with interest recently. Okay, let's come back to this tunneling itself.
Sorry, how is the nature of these gravitational waves different from the traditional black holes where?
Excuse me, I couldn't get your question.
How is the nature of these gravitational waves coming from these bubbles different from other more natural ones?
Different in some aspects. As you can easily imagine, gravitational waves emitted from these binaries have point-like source. So we know the direction, and we know the direction from which gravitational waves come. But if gravitational wave phase transition occurs in the early universe, then the whole universe is filled with gravitational waves propagating in every direction and various amplitude. So various frequency and various amplitude. So in that sense, these two are different. Okay. And coming back to the tunneling problem. So quantum tunneling, so let's simplify the setup. Let's consider quantum tunneling in vacuum in 1+3 dimension. This is just in order to simplify the argument. And the nucleation rate, gamma, per unit time, per unit volume, is known to be dominantly determined by Euclidean action of so-called bounce configuration, which I call pi bar. So tunneling rate is dominantly determined by this exponent, and this exponent of the summation, integration of the kinetic energy plus potential. And we know we can get this tunneling rate once we have this bounce configuration pi bar. But the problem is that it's a bit difficult to obtain this bounce configuration pi bar. So let me explain the procedure. This pi bar is obtained from this second order differential equation, second derivative plus first derivative minus potential derivative by the field equals 0. And this equation itself is not tricky, but what's tricky is the boundary conditions. We have to start this scalar field with 0 derivative. So this is a kind of scalar field moving in inverted potential. So we have to start this scalar field with 0 velocity, and we have to find a configuration such that this scalar field stops exactly at the top of the potential at time infinity. So you can easily imagine that this is very difficult calculation because if you start from a bit higher position, then this scalar field easily overshoot. And if you start from this lower position, then it undershoot. So you have to tune the initial conditions so that this scalar field stops exactly at the maximum. And in one-dimensional case, there are many approaches as shown here. But in typical cosmological or phenomenological situations, we have more than one scalar field. And if the situation becomes, your model has more than one scalar field, then this calculation becomes much, much difficult. And to me, this is something nonsense occurs here. Every time we have new particle physics set up, we or people recalculate this kind of equation of motion, though the potential shape is roughly the same for each case. Roughly the same means the potential has this kind of true and false vacuum, and we invert the potential and roll down the scalar field for many times. So it looks a bit nonsense to me. So the question is, can we use machine learning technique for this? So let me explain my idea. The main idea goes as follows. Potential is clearly an image, right? This is one example of two-dimensional scalar potential, phi1, phi2, and potential value. And suppose that your scalar field tunnels from the origin to this somewhere here. Then imagine drawing equal height contours for this potential. Then your potential looks like this. Then the problem reduces to image recognition problem. So this is cat-dog classifier example. If you have cat and dogs, then we human can easily label these pictures as cat or dog. And we know that machine can do the same job. So now the question is like this. You have potential, one-dimensional, two-dimensional, whatever. Then typically people solve bounce equation of motion to get bounce action or the tunneling rate. But in principle, since we know that machine works very well in image recognition, in principle, machine can tell what the value of this bounce action from this potential picture. And the interesting thing about this is that, okay, for cat-dog case, the way we recognize these pictures is not necessarily the same as the way machines do, right? It's okay. This machine do not have to recognize cat and dog as humans do, but it's okay as long as this machine performs very well. So the same thing applies. We human calculate the tunneling rate from this equation, but any good machine can calculate a bounce action without using this bounce solution. And it's okay as long as this machine predicts very well. Okay, now let me state the idea more clearly. Can we construct a machine which gives the bounce action for input potential V? That's the question. And if we can do that, there are several advantages. First, this will be faster than any other method because we know that neural network is almost linear algebra plus a small amount of nonlinear function application. And also, we can share, we means people in the community, can share the trained machine. And then the last item is what I mentioned. Such a machine does not have to solve equation of motion. And just as cat-dog classifier does not have to recognize images as humans do. So that's the idea. So I will explain the toy example. So I illustrated, in my paper, I illustrated the usefulness of machine learning using one-dimensional transition. So there's only one scalar field. Okay, let me explain the data taking process. I prepared 3 classes of potentials, C1, C2, C3. And class C1 consists of phi to 2, 3, blah, blah, to phi to 8 power. And for each polynomial, we have coefficients. And class C2 is defined as even powers of phi, phi to 2, 4 to 14, maybe. And class C3 is quadratic plus odd powers. And potential looks the same. Okay, I have to explain. I will consider only potentials which have false vacuum at the origin and true vacuum at 1 minus 1. This is allowed because in the calculation of bounce action, all these horizontal and vertical scales can be factored out. This is sample 20 potentials, and this right column is the distribution of the bounce action. And what I have to explain is coefficients, these A, N, are generated kind of randomly. And if you want to know it, please ask me later. And bounce action is calculated with traditional overshoot undershoot method. This is necessary because we apply supervised learning, so we have to first obtain the solution, the true answer. And each class contains 10,000 potentials and bounce actions.
Can you, what's this from on the right?
Excuse me?
Can you expand a little bit more the thing on the right? The
Expand? Oh, expand. Oh. I explain. Sorry. Bounce action. So if you have potential, you can calculate the bounce action by inverting the potential and using overshoot undershoot method.
So what's on the axis? What are you talking about?
Okay, this is histogram for the value of the bounce action versus number, and all this sums up to 10,000. Distribution of these 10,000s.
You have to evaluate the bounce action once you have the bounce solution.
That's the value of the
That's
axis.
the value, it's
Okay.
a real number. And that's for each of these.
Okay, now I'll explain the training process. Okay, this is my machine, and this is time direction. And the first step is training and test. And the second step is final application. And I'll explain. A training dataset is used for training, and test dataset is used in order to monitor that there's no overfitting. And after this step one, the machine is completed, and finally I will apply this machine. I will apply this application dataset to the machine. An example is like this: 8,000. So if we use C1 class, we give 8,000 data as the training dataset and 2,000 as the test dataset. And after completing the machine, I apply this whole 10,000 data to the machine. And permutation applies like this. And another interesting example is using all the mixture of three classes. If we do that, 24,000 data is the training data set, and the rest, the 6,000, is a test data set, and then we can apply this 30,000 data to the whole, to the machine. This is another example, and the final example is like this. We can construct the training data set from C2 and C3. Then, after training, we can apply the machine to, we can apply C1 dataset to the machine. This is a situation where this machine encounters some types of potential which this machine has never encountered before. And we can check the usefulness of machine learning with this kind of setup. And also, permutation also applies like this. Okay, so this is explanation for the data set. And for the machine, I will just use hidden layer equals 2. So this is really simple. This laptop is enough for the training. And input here. As I explained, what I will input to the neural network is image, but I will use kind of generalized image. A potential value, this is image part, and this is generalized part. I will also input first derivative and second derivatives, because I found that this improves the machine performance by a factor 2 or 3. This is input, and the output is the predicted value of logarithmic bounce action. Logarithmic is multiplied because we know from this distribution that this distribution is not symmetric, but after taking logarithm, the distribution looks somewhat symmetric. So this is just to enhance the training efficiency. Okay, and this is a very detailed node. I will implicitly rescale all the inputs and outputs to make the training much more efficient. Okay, this is the training process. I already explained. The error function I adopt is absolute value of the machine's output minus the answer. And output is logarithmic log of S4. And training is update of weights and biases. And this is further detail. I adopt mini-batch training. Suppose that this is the whole training data set. And one update, for each update, I give the machine 1/10 of the training data. This is called mini-batch. And this is 1 update, 2 update, 3 update. And 10 times of this process use the whole data. And this is called 1 epoch. And I trained the machine for 10,000 epochs. And I implemented this setup with TensorFlow. Okay, this is the result. First, case A, 1 class for training and test and application dataset from C1. And this is scatter plot for machine performance. S4 true value versus S4 predicted value. And we clearly see that the result is on this 45-degree line. So this means that prediction of the machine performs very well. And this right panel is the histogram for relative error for the bounce action. So it's centered on 0, and the typical error is within or order percent. And I tried 10 times of this machine construction and took average of this delta S4 over S4 for the 10 trials. And the resulting error value is sub percent, 0.006 or something. So this works very well.
So what's the error on just the test data?
Excuse me?
When you just use the test data, what's the numbers? So the numbers you quote is for 10,000 or for 2,000?
10,000. Okay. So these training and test data sets are used for training and monitoring. And at this stage, at this point, machine is already completed. And then I apply this test on 10,000 data to this machine. And this is the value from this 10,000 data.
I'm curious how well it's performing on unseen examples.
So I will explain later. This is the first example. So if the potential, all the potential comes from the same class, the machine performs very well. And same thing applies for C2 and C3. The error is still sub percent. And by the way, this training is less than 1 minute with this laptop.
But do you end training after, so this 10,000 epochs or however you had, is this fixed by this absolute number, or is it fixed by the point at which it performs much better on the training data than it does on the test data?
I'm sorry, I didn't get your question, but this.
So if you check on the test data how well it performs, and you check on the training data how well it performs, at some point you will start to not perform better on the test data, but you can still perform better on the training data. And at that point, you usually stop training.
Okay, yeah, so that's. I should have done that. But I just, in this study, I just fixed the training epochs, and I just cut the training process at this epoch, and I checked at this, during all the training process, I checked that the performance for the test data is not much better than training data. Yeah, so not much. Yeah, worse. Yeah, that's it. Yeah. And another interesting example is a mixture of 3 classes, and the result is still sub percent, 0.005, so 0.5%. Now, your interest will be the situation where this machine encounters potential which it has never experienced. This is the result. As we expect, the error, the value becomes a bit worse, 2%, but still works well for this poor laptop.
But they are a little bit similar, right? I mean, I can't remember quite now, but C2 was all the even powers, C3 was all the odd, and C1 was odd and even. So it has seen potent with only even powers, potent with only odd powers, and then it puts together this information to predict something on the C1 which had even and odd powers. Is that right?
I'm sorry. Could you
Can you remind me what C1, C2, and C3 was?
Yeah, you're right in the definition of C1, C2, C3. Like this.
Okay, so it has seen potentials that only involve even powers,
Even
and it has seen potentials that only involve odd powers, and it manages then sort of to get something which combines the two.
To get class C1. Then we can check the next slide because so let's see this example. The training and test are from C3 and C1, and this cannot construct C2 class, right? Odd powers and lower power polynomials, and this C2 contains higher even powers of polynomials. But still, in the previous result, the error was 2%. And in this case, actually, the performance improved. And I know the reason, but it's a bit detailed. Anyway, for all the cases, and the last case is this, and it's sub%. So for all cases, the machine performs very well. So I illustrated the usefulness of machine learning to this problem. And the question is like this: how much precision can we expect in practical use? This is my toy setup, so we have to try more seriously. And potential shapes in particle physics phenomenology are not that many, actually. For example, quadratic, cubic, quartic, or quadratic and logarithmic, and there are only several patterns, I expect. So if we train with all this type of all these kind of potentials, then the resulting precision will be at least C1, C2, C3 case. And another question is how much is the speed up? And our traditional overshoot undershoot method typically takes 1 to 10 seconds in my code. This is just because my code is poor. Other approaches take order 10 to minus 2 seconds. I learned it from private communication. And our machine takes order 10 seconds for training, but after training, it takes only order 10 to minus 4 seconds, so it's a significant speed up. And okay, now I will talk about generalization. In this paper, I just discussed a single field case, and generalization to different space-time dimensions. This is relevant for example, thermal phase transitions, and this is trivial because we can just change 3 to 2. And another question is multi-dimensional transition. This is difficult, and we need good ideas for that. And this is ideas which I came up with. First, for two-dimensional case, convolutional neural network may help, as the previous speaker explained. The convolutional neural network is like this. Special method for image recognition. We first convolute the original image with this smaller image like this, and then we connect this to usual neural network. And in our case, we can convolute like this, or another idea is convolute like this, because we know that transition occurs from the origin to the outward region. So this may help. This may work better, but I don't know because I haven't tried it. And another idea is to replace the one-dimensional calculation part in the existing code with our method, machine learning method. This may be more realistic, so I will try this first. And another idea is that machine learning may also be used for initial position suggester for the bounce equation of motion calculation. Anyway, let me summarize my talk. So calculation of quantities from scalar potential can be regarded as image recognition problem. So this may apply to, for example, inflationary physics or all the scalar field dynamics. So we can construct a machine which calculates any quantity from scalar potential just by using image recognition technique. And we propose using this technique for bounce calculation. And I illustrated the usefulness in one-dimensional transition. And I explained possible ideas for generalization. Thank you very much.
Congratulations.